Okay, section 1.2, mathematical models, a catalog of essential functions. So there are some basic graphs that you should remember from pre-calculus. You should know how to graph. In later chapters, chapters 3, we will be using techniques of calculus to have us graph. Sorry. Sorry. To have us graph functions. And so even though I'll be giving you the techniques to graph functions, what? I'll be giving you the techniques to graph functions. You should still know what these functions look like, the graphs of these functions look like. So the graph of power functions first. The graph of y equaling x to the n, where n is a natural number greater than 1 and some even natural number. Well, if I have the graph of y equal x squared, it looks like some parabola. If I have the graph of, let's say, y equaling x to the fourth, it will have this same sort of general shape, but it won't be quite parabolic. It'll be more, well, square-like almost. And say y equaling x to the 50th will look even more sort of squarish looking. Next, let's look at the graph of y equal x to the n, where n here is an odd natural number, not equal to 1. And so some odd natural number greater than 1. Then, well, look at the graph of y equal x cubed. It has this sort of sigmoidal shape. The graph of y equaling, let's say, x to the fifth will have the same sort of general shape. But again, it'll be more box square-like. The graph of y equal x to the 51 will even be more sort of box-like. Next, the graph of, well, the nth root of x, where n is even, will look like, well, this parabola where we've sort of, this curve here, where I've just sort of toppled it on the side. So rather than looking like this, I've toppled it on the side and I've gotten rid of the bottom portion. So it just looks like this portion here, where I've flipped it about the x and y axis. So then it looks like this. And so this is the graph of y equaling nth root of x, where n here is some even natural number. The graph of y equaling, well, the nth root of x, where n here is some odd natural number greater than 1. Then it looks again the same as this, but again, I flipped it with respect to the x and y axis. So I've just taken this and flipped it over and then flipped it over on this side. So it looks like, so this now looks like this. And this guy here looks like this. And so it looks, well, like this, but I've sort of interchanged the x and y axis. The graph of y equaling x to the first power. Well, it's just the line y equal x. The line of y equaling x to the 0 power, just the graph of y equal 1. The graph of y equal 1 over x to the n, where n is odd, looks something like this. Again, as n keeps getting larger and larger, it looks more square-like. The graph of y equaling 1 over x to the n, where n is even, looks something like this. N is an even integer. The graph of, well, y equaling x to the m over n, where m over n is, well, some fraction, looks more and more, looks sort of like somewhere between these guys and these. And it may either flip over or it may have nothing on this side, depending on if you're trying to take even roots of negative numbers. So in this case, I've flipped it over. So if this is x equaling y equaling x to the m over n, where m over n is reduced, m is even, n is odd, and m is less than n, then it looks something like this. Again, it's just sort of a merger between these guys here, well, which is the same as these guys. I'm only looking here in the first quadrant, depending on how big each of these are. If they're bigger than 1, it looks more or less like this. If it's less than 1, it looks more like this. And if you're trying to take even roots of negative numbers, if you have trying to take even root, then these guys are going to go, you won't have anything over here. If you're trying to take like odd roots, then you will have something over here. And it'll either be up here or down here, depending on if it's symmetric about the y-axis or symmetric about the origin. Okay, like in this case. So y equaling x to the m over n, where m over n is reduced, m is odd, and n is odd, and m is less than n. Next, the absolute value. And so the graph of the absolute value looks like, well, a V. It looks like the graph of y equal x in the first quadrant and the graph of y equal negative x in the second quadrant. The graph of x squared plus y squared equals I squared is the graph of a circle centered at the origin of radius r. This is not the graph of a function. So in this case, we're not graphing a function. It doesn't pass the vertical line test. An algebraic function. If you take some constant, so number, and you take a variable, you add, subtract, multiply, divide, take a power, take a root, do this a finite number of times to these real constants into these into the identity function, then you get what we call a algebraic function. We'll be studying things like algebra. So f of x equaling x to the 2/3 plus x to the 4th over 2x plus 7. That's an example of an algebraic function. At the beginning of this course, we'll be studying algebraic functions. In general, in this course, we will not study non-algebraic functions, which are going to be called transcendental functions. We'll not be studying transcendental functions, and that's because of the addition of calculus that we chose. We chose the one that's late exponential version, so the late transcendental functions. However, strangely enough, they do give us some, they still, even though they say they're not doing exponentials, they do give us exponential functions in a different guise. And so examples of transcendental functions are either, well, you really only know one example of a transcendental function, the exponential function. And so the exponential function, e to the x, is, well, a transcendental function. And the inverse of it, ln of x. So really just e to the x. And the trigonometric functions, sine, cosine, etc., which turn out to be actually just in disguise the exponential function. Well, exponential function for a complex coefficient, for an imaginary coefficient, turn out to be sines and cosines. Or another example of a transcendental function is things like cosh and sinh, the hyperbolic trigonometric functions. But again, these hyperbolic trigonometric functions are really just e to the x in disguise. So really the only transcendental functions that you really need to know is e to the x, or actually in this case, let's say ln of x. And it turns out that we will, not in this course, but in Math 262, discuss ln x. But in this course, we actually discuss sine x, and we actually discuss some trigonometric functions, even though we're not supposed to, because that's involving this guy. And a little bit of the hyperbolic trigonometric function. Again, even though we're not supposed to, but we do. Okay, so let's recall some things involving trigonometry. So suppose I have a ray. So it starts at some point and it goes in some direction. So let's call this ray A. And let's suppose I have another ray B that starts at the same point. We'll call this coincident sort of point the vertex. And so A and B start from the same point. There are two rays start emanating from the same point, called the vertex. Usually denoted, well, so this is my vertex. And I will call one of these rays, the initial side, and the other ray, the terminal side. So let's suppose that this ray here is my initial side, and the ray B here is my terminal side. I'll measure an angle starting at the initial side, ending at the terminal side. I'll denote this angle by theta. So theta is equal to the angle from A to B. It's the angle of this AOB. The standard position. The standard position is, well, let me write a coordinate axis. We will assume that the vertex is at the origin and the initial side is the positive x-axis. If we measure the angle in a counterclockwise direction, that will give us a positive angle. If the vertex is at the origin and the initial side is the x-axis, we say that this angle is in standard position. Now the question is, well, how do I measure this angle? Well, one way is in degrees. And so there are 360 degrees in a full circle. Why? Well, this goes back to ancient times. And so there are it goes back to the fact that the Babylonians did everything in base 60. Why base 60? Because base 60 is actually a very easy sort of system, numerical system, where you don't have to deal with, if you deal with fractions, it's very easy to deal with most fractions. 60 is divisible by 2, 3, 4, 5, 6. And so it's the smallest number divisible by 2, 3, 4, 5, 6. And so because of that, it makes a lot of the smaller fractions easy to deal with. And so base 60 just turns out to be easier because of that. Next, there are 360 days in a year. So if you look back in the Babylonian calendar, there are 360 days in a year. If you look at banks, in banks, there are 360 days in a year. So whenever you're doing calculations involving banks, it also is 360 days in a year. There are like 5 days of celebrate. There are 5 additional days of celebration that you didn't count as a day. So there are 360 days in a year. Therefore, there are 360 degrees in a full circle. There are 60 minutes in a degree, just like there are 60 minutes in an hour. There are 60 seconds in 1 minute. Well, I should probably say this. There are 60 minutes of arc in 1 degree. There are 60 seconds of arc in 1 minute of arc. So there are 60 seconds of arc in 1 minute of arc, just like there are 60 seconds in 1 minute. Usually we don't say of arc because it's obvious from context that we're talking about an angle rather than talking about time. But if there is any sort of confusion, then we say of arc. So rather than just saying 60 minutes, we'll say 60 minutes of arc if you are confused that this is an angle. Because obviously minutes and seconds, these are all the same as what we use for time. Well, notice that for time, we also have sort of the same, we use the same system that the Babylonians did. And so there's 60 minutes an hour, 60 seconds a minute for time also. Gradians. So another measure of, an angle, gradients. These are used only by American engineers, civil engineers. So if you're in civil engineering and you're an American, you use gradians. There are 400 gradians in a full circle, and there are 100 gradians in a right angle. So they use that because 100 is easier to deal with than 90. So in our base system 10, 100 is easier than 90. If you're doing base 60, actually 90 is easier. So in the base 60 system, actually the 90 makes sense. That's actually easy to deal with. But in base 10, 90 is not as easy to deal with. So for American civil engineers, they use gradients, 400 gradients in a full circle, 100 gradients in a right angle. Next, radians. Well, these were sort of previously the gradians and the degrees were just sort of arbitrary. They really made there was no geometrical reason why we should pick 400 gradients in a circle or 360 degrees in a circle. It really was just sort of arbitrary. Had to do with the days that the Earth travels around the sun. So that really had nothing to do with geometry. So what we do in this class is we use radians, which has a geometric definition. So there are 2 pi radians in a full circle. Next, if I look at a sector, meaning I take a full circle and I slice it into a little piece. So say we have a pizza pie here. So we have here this pizza pie, and we slice it into some pieces. So this is a slice of pizza. And we measure the radius here of the pizza and its arc length. There's a relationship, easy relationship, between the angle, when written in radians, the radius of your circle, and the length of your arc for this sector. And so the arc length. The arc length, S, is equal to the radius, R, times the angle theta. So long as you're measuring in radians, this is a very easy formula to determine the arc length of a sector. Next, the area of the sector is 1/2 r squared theta. In calculus, all of our so the reason that we use radians is that all of the formulas are much easier when dealing with radians as compared with using degrees, gradients, etc. So from now on, I will always assume that everything is written in terms of radians, unless otherwise specified. So if you do not see that I'm saying that it's in any particular measurement, assume it is in radians. 180 degrees, so half a circle, 180 degrees is pi radians. Therefore, 1 degree is pi over 180 radians. And, well, taking the reciprocal, 1 radian is therefore equal to 180 over pi degrees. Let's consider trigonometry, which is the ratio of the lengths of sides of a right triangle. And we will define a function of the angle in terms of these ratios. And so the cosine of theta is adjacent over hypotenuse. So A here is the length of the adjacent side. O here is the length of the opposite side, the side opposite the angle. And H here is the length of the hypotenuse, the side opposite the right angle. And so cosine of theta is the length of the side adjacent divided by the length of the hypotenuse. The secant of theta is its reciprocal, the length of the hypotenuse over the length of the adjacent. The sine of theta is the length of the side opposite over the length of the hypotenuse. The cosecant of theta is the length of the hypotenuse over the length of the opposite. The tangent of theta is the ratio, the length of the opposite over the length of the adjacent. The cotangent of theta is the length of the opposite over the length of the length of the adjacent over the length of the opposite. Recall that you can define right angle trigonometry in terms of a circle of radius r centered at the origin for some coordinate system. If a point xy is on the circle. Then I can associate with these coordinates of your ordered pair the following trigonometric function. And so cosine of theta is x over r, secant theta is r over x, sine of theta is y over r, cosecant of theta is r over y, tangent of theta is y over x, and cotangent theta is x over y. Now, of course, my assumption here is I'm never dividing by 0. So for each of these, make the assumption that the denominator is not 0. We have the following identities. Cosecant of theta is 1 over sine theta. Secant theta is 1 over cosine theta. And tangent of theta is sine over theta over cosine theta. So that means that we can rewrite our trigonometric, well, these are the common 6 trigonometric functions in terms of just 2 other trigonometric functions, sine and cosine. There are several other trigonometric functions that are not nearly as popular, like VERS and things of that sort. They're not nearly as popular anymore. Cotangent of theta is 1 over tangent of theta. So I can write cotangent of theta as cosine of theta over sine of theta. And we have the Pythagorean theorems. Cosine squared theta plus sine squared theta is 1. So if this is theta, and I have 1 for the length of the hypotenuse, then the length of the adjacent is cosine theta. The length of the opposite is sine theta. Next, we have that tangent squared theta plus 1 is secant squared theta. And so if I let the length of the adjacent be 1, and the length of hypotenuse, secant theta, the length of the opposite tangent theta, then by Pythagorean's theorem, we have the tangent squared theta plus 1 squared is equal to secant squared theta. And lastly, we have cosine squared theta plus 1 is cosecant squared theta. So if 1 here is the length of the opposite side, then the length of the adjacent side is cotangent theta, and the length of the hypotenuse is sine cosecant theta. You can see each of these by divide each side here by sine of theta to get this triangle, and divide each side here by cosine theta to get this second triangle. So again, by Pythagorean's theorem, you have the cotangent squared theta plus 1 is cosecant squared theta. And we have that cosine is an even function and sine is odd function. And so cosine negative theta is cosine theta. Sine negative theta is negative sine theta. Tangent negative theta is negative tangent theta. So tangent is an odd function. Secant negative theta is secant theta. So secant is a even function. Cosecant negative theta is negative cosecant theta. So cosecant is an odd function. And lastly, that cotangent of negative theta is negative cotangent theta. And so cotangent is an odd function. We have the sum and difference formulas for trigonometric functions. Sine of u plus or minus v is sine u cosine v plus or minus cosine u sine v. And cosine u plus or minus v is cosine u cosine v minus plus sine u sine v. We also have the double angle formulas. The sine of 2u is 2 sine u cosine u. This will be very important for actually math 262. Yeah, much more important, 262. And similarly, the cosine of 2u is cosine squared u minus sine squared u, which is equal to 1 minus sine squared, 1 minus 2 sine squared u, which is equal to 2 cosine squared u minus 1. These will also be, this one will be very important also in Math 262. From which we get, well, the half angle formulas, which again in 262 you must know. Sine squared u is equal to 1/2 times the quantity 1 minus cosine 2u. And cosine squared u is 1/2 times the quantity 1 plus cosine 2u. There are two commonly used triangles that you should have memorized. The 45-45-90 triangle. And so the length of the adjacent and opposite are 1, and the length of the hypotenuse is radical 2. Again, you could have learned it in other ways, but at least so I don't have any fractions. The 30-60-90 triangle. So the length, so this is, well, 60 is here. So the length of the adjacent to the 60 is 1. Length of the adjacent to the 30 is rad 3. Length of the hypotenuse is 2. So let me do some examples on page 33. I'm switching. Okay. Oh, here it is. Switching computers. 1.3. 2. Page 33. Find the domain of the function. Problem number 5. F of x is equal to cosine x divided by 1 minus sine x. So I want to find the domain of that function. So I don't want to divide by 0. And well, I want to be sure that well, I'm never divided by 0. Uh-oh. Sorry. 1 second. Let's see why this is not charging. There. Okay, sorry. I wanted to be sure that my computer didn't die immediately. So let's find the domain of f. So notice that cosine and sine are defined everywhere. And so I don't have to worry about when cosine and sine are defined because they're defined everywhere. So the only thing I have to worry about is dividing by 0 when I'm considering the domain. So I want to see, well, when is the denominator 0? When is sine of x is equal to 1. And so let me draw this. Okay. I'm just scrolling. And let me draw this situation here. So I have a unit circle here, centered at the origin. I'll put a Y here. So maybe I'll put it in red. I don't want to be at the top of this circle here. And so I don't want to somehow find my way to be on top. So if I look here, maybe let's copy this. Just copy this for a second. Okay. So I don't want to be here. Somehow I don't want to land where I'm at the very top. What's going on here? Okay, so I don't want to land up here. So somehow I want to go and be here, but maybe okay. Sorry, I have to get control back to my computer. There it is. Just trying to get control back. So maybe I start here, but maybe I go around the circle a few times, come here, and maybe start on this, go this way, or maybe start here, go around the circle a few times, stop there. So somehow I keep going around the circle and end up here, and I don't want to. So I've got to get rid of those. So my domain okay, there. So I don't want x to equal pi over 2, which is this angle here. So starting here, ending here, that's a pi over 2, plus, well, going around the circle, say 2 pi, let's say k. And so for any k, which is any integer, because it could be that I'm going either clockwise or counterclockwise. And so my domain and I'll use this coset notation, is a set of R without pi over 2 plus 2 pi z. So let me give you a left coset notation. So if I have some number, A, plus a set B, this is just the set A plus B, where B is in the set capital B. This is called a left coset. And it's because the number here is on the left. And we also can do I guess I wrote them both as a left. So this is a left additive coset. And I could also write it this way as a left coset. Say AB, where B is in the set B. Okay, there. Just waiting for my computer to allow me to do something. There it is, where B is in the set B. So this is another left coset. So I've used the coset notation.